So we did talk about queries a little bit in SQL, right? And I did mention the problem we have about record linkage, yeah, and key anonymity as a way to potentially solve it. And I mentioned at some point that there was a way to do a join operation, and I had some code for this join operation, and actually this join operation did work. So something wrong here. Okay. Sorry. Oh, something wrong. That's weird. Okay. I don't know what's wrong here. Verbatim. Where is the verbatim? So I'm going. There was something weird happening. Anyway. Okay. Fine. Sorry about this. Now I have a weird thing with the slide for join, but the join code I showed you yesterday does work. So basically, I don't know why it wasn't working yesterday. So database join. Let's make it big. So as you can see here, the code says very simply that you have these two databases. Okay, here it's very easy to do the linkage because even with one column you have identical column on the other side. So, but you can do the same if you had multiple columns where you could join one of them. So here this thing just works. So select the rows from both of these things where those things are equal, and it's about basically cluster join. Okay. So you could do the AND and say and other attribute is the same as another attribute, and it works. Okay. Yeah. So we would like to avoid that, and one way to avoid that is key anonymity, right? And key anonymity basically groups people so that basically every row in the database, apart from if you ignore the result column, repeats at least k times. So that's the idea. Which is okay, but we saw also the definition of differential privacy, right? And differential privacy specifies something specific. It says that the probability of seeing specific output for the same data, right? If the data slightly changes, shouldn't change very much. Yeah. So then the question I put to you right now is, do you think k-anonymity is a concept that satisfies differential privacy? And if not, do you think you can make it so it does satisfy differential privacy? Okay, you don't have to go through the math, just think about it in terms of what is the basic property of differential privacy. Yeah. So what is k-anonymity? Let's walk through this very slowly, okay? So k-anonymity is a mapping, or is a property of the data, right? Yeah. So what is this property? It says that the data should have, let's say, basically some records repeated, right? Okay. So if you have a data set that doesn't satisfy this property, then you can have an algorithm for generating a new data set, right? Yeah. So the question is not so much about the data itself, it's about the procedure that generates the k-anonymized data. Yeah. So the only way that we can make k-anonymity differentially private, k-anonymity itself cannot be differentially private, because it's just a definition about what you see right from the data. It's about the procedure that generates this k-anonymity data. Yeah. So the procedure has to satisfy this differential privacy property, so it means that for slightly different data, where I just change the data of one person, or remove the data of one person, then the output with the new database should somehow, seeing a specific output should have almost the same probability as when I don't change the data. Yeah. So if you're talking about probabilities, that implies one thing directly. What does it imply about the algorithm? Does it have to be, can it be a deterministic algorithm, or does it have to be a stochastic algorithm?
Should be stochastic, right?
Yeah, it has to be stochastic. Right. So let's think about it more generally. Okay, so why do we need stochastic algorithms for differential privacy? Yeah. So let's say you have a set of possible data sets. Okay, so this is your set of possible data sets. Okay, it's very big. I can't make anything bigger on this paper, but it's very big. And let's say you have an algorithm that's very simple. Okay, it basically, if the data comes from this subset x1, then it maps data to a point here, y1. Okay. If it comes from here, anywhere there, then it maps the data to this point here. Okay. So in that sense, what you can learn if you just know that the output is y1 or y2 is that the data came from either this set or that set. So it's not a lot of knowledge, right? Okay. Let's say that you know something more. Okay. Let's say that you know that the data either came from this point here, this point here, or it is some point there. Okay. Then by seeing the output of the function, you know whether it's this point or that point. Okay. And that's the reason why you need basically randomization. If you randomize the output of the function, then even if you already know that it's either one of these very specific points, then you just slightly increase the probability or your knowledge about what's the right point. Okay. So that's the basic idea here. And to put it in the Bayesian framework context, by ensuring that if the algorithm is differentially private, then it ensures that no matter what happens, the probability, the posterior probability you have about any specific data will never become 1. You always have some uncertainty. And you can always bound the amount by which you will increase your certainty about what the data is through differential privacy. Okay, so that's the kind of intuition-related questions. Let's go to the presentation a little bit more. So last time we talked about a very simple mechanism, the random response, right? So the original algorithm was slightly different, but I think it's sufficient for us. Okay. And we also mentioned that it satisfies differential privacy definition. Okay. So now let's talk about something slightly more general. Okay, you have response policies. Yeah. So you have a database, you access it like in the SQL model, and then you get a response back. And so you don't necessarily put all the data out in a randomized way. You just have some query that you do, like, I want to count the number of people that have blonde hair. Okay, something like this. So you can imagine, it's not necessarily true, but you can imagine that you had a magic differential private select function in SQL, which for a given additional input epsilon and everything else the same as before, it basically returns the query result by also satisfying differential privacy. So you can think of all these specific queries as algorithms, where you're selecting one algorithm to run by specifying a statement here. And each one of these algorithms, because you say epsilon there, will satisfy epsilon differential privacy. Okay. Now the question is, if you ask many questions from a database, how much privacy can you guarantee, right? So if I ask, for example, how many people, well, if you can ask the same question 10 times, for example, and each time you get a different answer, because it's randomized, then in the end you can actually probably figure out what is the noise-free answer, right? Yeah. Okay. So if I ask you to take drugs, you throw a coin, you do the procedure, you say yes, no. Do it again, do it a million times, in the end I will know the right answer. Yeah. So this is what is called the composition property of differential privacy. Yeah. So no matter what, in what order you ask queries, and no matter if the next question you ask from a database is actually dependent on the previous answers and questions you had, then if every time you get a response, the response comes from an epsilon differential private mechanism, then at the end the total privacy loss, or the compound privacy guarantee for the whole thing is epsilon t. So it tells, okay, so you have this bound, but you cannot guarantee anything more. So that means that at some point you will probably lose more privacy than you should be able to withstand. Okay? So there's a formal theorem about this, but we don't really need to go through it. Specifically for the epsilon differential privacy, it's a pretty nice and simple idea. Okay? Now, so far we have been talking about one attribute, and it also makes sense to think about more than one attribute, right? Yeah. So if you think about the randomized response mechanism, let's say instead of just generating the data directly, you ask for every individual person one question, right? Okay. So what is your height? What is your age? What is your weight, etc. So if you want to be epsilon differential private with respect to each one of these questions, well, you can be, but if you ask 5 of these questions, then you will be 5 times epsilon differential private. Yeah. So if you have many attributes for a person and you want to protect them using randomized response, then the simplest way to achieve it is to say, okay, I have k attributes, and I want to be epsilon differential private, so I need to be epsilon divided by k differential private for each one of these responses. But if some of these are more sensitive than others, then you might want to say, okay, have a small epsilon for the really sensitive ones and a big one for the less sensitive ones. Okay? Okay. So now we still stay in a case where epsilon differential privacy is thought about with one attribute per person. So have n persons, and one person's data is different. So here we say that this is one possible data set, and this is another possible data set, and here the value of xj changes. So these are the definition of neighborhood in this particular scenario. And the adversary has a prior that the data is either this one or x prime. So the total probability of these two is 1. So it's exactly the scenario that I sketched on the paper. there are many possible data sets, but the adversary knows it's either one of those two. Yeah. So then, what do you think we can say about the posterior distribution of the adversary after have seen the output, no matter what the output is of the mechanism? So we know the output is epsilon dp. We don't know exactly how the mechanism works, and we don't care. We just have two possible values for the data, and we know the mechanism is epsilon differentially private. What do you think you can say about it? So, if you just write a definition of posteriors, it will probably work. But I will probably do it on the paper here because you probably cannot guess what should be done. So, let's see. So what we have here is basically, let me just make this bigger. So we know that, so we have some prior for x, right? Okay, fine, and we know that this is 1 minus our prior for x prime, right? Okay, and we can write the posterior for x given some specific output from the mechanism, okay? And we know that this is basically just probability of x given a. Yeah, we assume here that the adversary knows the mechanism, so he can just plug this in there. And the prior probability of x, right? And then we divide by the same thing. Oops, this is the wrong way around. Probability of a, right, given x and prime times. Okay, so this is basically it. So now we see that if we change, so you have x prime there, so we could basically, because we know the mechanism is differentially private, we know that p of a given x is smaller or equal than p of a given x prime times e to the epsilon. That's the definition. So if you remember, this is the same as saying that ln p of a given x, p of a given x prime spanned by epsilon. It's the same thing.
It says pi of x given a and not a.
It should be a given x, yeah.
Okay.
Yeah. P of a given x. Yeah. Okay. So we could just plug this in and we see something, but it's more informative if we look at the ratio of the two things. So x given a divided by, so this thing here, it basically becomes this, right? Times this, and this times this. And the denominator is the same, so it cancels out, right? Okay, and we know, for example, that this guy and this guy are the same, apart from the fact that there's an epsilon factor. Yeah. So we know that now the posterior ratio that we have, so the probability of x given a over the probability of x prime given a, is bounded by the original prior ratio, yeah, times the constant, and the constant just depends on epsilon. Yeah. So this guy here is just so this is how much you think x is likely relative to x prime, and this is how much you think x is likely relative to x prime given the data, yeah, given the observations. And you can see that this ratio only increases by a factor of exponential to the epsilon. So when epsilon is 0, it stays the same. Yeah. Okay. So this is like the posterior view of the differential privacy. And this holds for any mechanism. You don't have to really say anything about x being 0 or 1 or anything like that. Okay. Okay. So, as I mentioned before, when you have multiple attributes, we need to deal with them in some way, right? And this is not super trivial because every released attribute is kind of like a new query. Yeah. So when you add noise, you have to think about how many attributes are going to be released. So if I know I'm just going to release your age, then I add this amount of noise. But if I know that I'm going to release also another 1,000 attributes about you, then I have to add 1,000 times more noise to the age. So that makes things difficult if you want to release high-dimensional data about people. As I give you an example that's very stupid, imagine that I release 1,000 variables, but each one of them is a deterministic function of the previous one. So if you know one of them, you can calculate all of the others, right? So that's why you need to do that, basically. But it's kind of important, and you need this for the exercise. So you need to scale about the number of attributes. Okay, so far we talked about one specific mechanism, the randomized response. Now we'll go to the second one, and this is the Laplace mechanism. Okay. The Laplace mechanism is very simple, and it basically says you have some function that you want to calculate. Okay. Let's say I have data from everybody of you, and I want to calculate the average salary. That's one attribute. I don't care about anything else. And now, instead of just adding noise to individual salaries, maybe I would think about adding noise to the end result. Yeah, maybe it's better. Or the other way around, let's say you have you get a salary which is not just 0 or 1, it's some other variable, or continuous variable like the salary. So then I would like to add noise to each individual variable. But then I cannot use randomized response because it doesn't work for this infinite domain. So what can I use? Well, you can use the Laplace mechanism, which is applicable to every real valued vector function. So here we just define for one-dimensional data. But if you have one-dimensional data, basically adding Laplace noise can satisfy differential privacy. Okay. So if you remember, basically the Laplace density is the same as the exponential, more or less, as a symmetric exponential function. Yeah. So the exponential decays with this parameter lambda. So the larger this is, the more variance you have. So lambda squared. And in this case, we also have the mean. And the mean is the mean of the function we would compute. And the variance is lambda squared. Now, if I just want to report your data, right, then the f function is just the identity function. And we just add noise to the data directly. Your salary plus Laplace noise. If the function is something else, like the mean salary, then you can calculate the mean first and then you add noise. So it's a very simple mechanism. So this is the thing we want to do, basically. Let's say the ith person receives a salary, okay, xi, and we want to calculate the average salary in a private manner. We have two choices. One choice is to do what I mentioned before. Every person has a yi, which is basically a noisy version of the salary, where omega is always coming from Laplace noise. And then we return the average of these yi's. Okay? That seems fine. And then the second is have a centralized privacy model. And then in this privacy model, you calculate first the average, and then you add some noise. Okay? So then the question is, how should we add the noise to achieve a specific privacy level? Yeah. probably is not very clear from this, right? Yeah. I just want to, before we go through it, I will go through a small example. So let's say, so the second model is basically what is called the centralized privacy model, because to calculate this function, right, somebody has to have the data, yeah? And you cannot just share the data among yourselves. So you have to give the data to somebody you trust, and then this person calculates the average and adds the noise. So you trust them to add the noise when they calculate the average. Okay, so it's a matter of trust. What you are trusting? Are you trusting the people that process your data to do it properly? Yes or no? If you don't, then this type of model doesn't work. You have to add noise to the data before you send it. Okay? If you do, then this is a fine model. And actually, we will see that it's a pretty good case. Fine. So how much noise should we add? Well, it's not a trivial question. So the first thing you have to check when you think about how much noise you should add with using this mechanism is what is the sensitivity of the function you are computing. Okay? And does anybody know what's the Lipschitz property? Yes. It's the same thing as Lipschitz. For those of you who don't know what's Lipschitz property, then I will just write it down. Okay. So imagine you have a function, right? Continuous function. And you basically can calculate the gradient of the function, the derivative, right? So there's a point where the derivative is maximized, yeah? So if I plot the derivative of this function, basically it goes up and then it becomes 0, then it's negative, then it becomes 0, then it becomes some constant, and so on. And if I look at the absolute value of this derivative, it's kind of like this. And the maximum of the absolute value of the derivative is Lipschitz, the Lipschitz constant, or the smoothness of the function, or in this case, the sensitivity of the function. Another way to think about sensitivity is you have this function here, and you look at a cone that you move around the function, so that no matter where you move this cone, all the other points in the function are within the cone. Yeah. So if I move the cone there, then all the points are there. If I move the cone here, then all the points of the function are there, and so on. Yeah. So you have this function here, and this particular cone, if you move it anywhere in the function, it contains every point in the function. Okay. And the slope of the coin is the sensitivity. Yeah. This works okay for continuous functions, but in general, we might not deal with continuous functions. So we have, let's say, a function like this. Okay. So you cannot define gradients and stuff, but you can still use the idea of the cone and say, okay, well, for any neighboring points, right? So you have a neighborhood here now. Let's say I connect some points. Okay. So the connections are the neighborhood. Okay. So for any connecting points, I want the difference to be not more than L. And this is basically the definition of smoothness in this case, right? So for our case, points are databases, and neighboring points are databases where data of one person has changed, or has been removed, or added. So this is the definition of neighborhood. But you can think of it as smoothness. It's kind of more convenient. Okay. Now, neighborhood in general is a problematic thing to work with because you have to define what is a neighborhood in order for you to be able to say something about the privacy that you're talking about. Yeah. So depending on how you define neighborhood, you have different privacy concepts. I will give a short example now. Think about your smart meter. Maybe you have one for electricity that sends your consumption to some provider, or your Google account sending data to Google. Yeah. So you can say that every day I add some noise to my data, right? And I send it to Google. But what we have seen from the The question is, do we consider the data of each day to be like a separate record? So neighborhoods would be, the data is always the same, but I change the data of one day. So then you provide privacy just for the data of one day. Or do you say it's my whole data for the whole time that I exist that I want to protect? It's a different thing, right? So if it's the second, then you need to consider the noise that you should add to protect privacy with respect to your data being in the system at all, yeah, or being in the system, compared to the case where you remove your data for 1 day or 1 hour or something like that. Yeah? Obviously, if you just think about data for 1 day or 1 hour, it's probably less noise, right, that you need to add. Remember this composition theorem? So if you say that you have your data and you ask queries about you for every possible second, and every time you ask a question and you get a response, you lose some more privacy. Yeah? So obviously it's not the same thing. Yeah? So if you define neighborhood in terms of your whole life and woo-woo, then the noise you should add is probably too much for it to be useful. If you think about it in terms of your data in a particular day, then it's slightly different, right? And basically Google is doing the latter thing, more or less. So anyway, the sensitivity is important. Why? Because if you think of the function as being a calculation on some sensitive data, then the more the function changes when you change the data, yeah, the more noise you should add. So it should hide the change in the function, so to speak, right? If I change the data and from 0 it becomes 1, then it's okay. It's a relatively large change, but not so much. If when I change the data, it can change from 0 to 1 million, then obviously it's easy to detect if you add the same amount of noise. So you should add more noise depending on how much the function changes. And you should basically add noise proportional to the sensitivity. Yeah. Okay, so just 2 examples here. The first one is what happens if your function is just a bounded function of some real number. So you have a number and you map it from 0 to b. So it could be anything in the real numbers, but you just map from 0 to b. In that case, the sensitivity of your function is b, because if you change the data, it can go to 0, it can go to b, but it cannot be any other value greater or smaller, so the sensitivity of the function is b. Yeah. So this is an interesting case where you have one individual and one attribute, and you say I want to add noise to this attribute. So then the sensitivity of this function is basically the range of the attribute. Now, what about the case where you have an average of one attribute for many people? So you have n people, and you know that the attribute is ranging from 0 to b, so you have some bound. And now you're going to calculate the average, which is also bounded, of course. Yeah. Then what is the sensitivity of this one? Since that yeah?
Do I guess b divided by n?
Yeah, sure. Yeah, exactly, that's it. Because you basically can just write f of x and f of x prime, subtract one by the other, and all the terms cancel out apart from the one that has changed. And this one changes by bound b, and then you divide by n. So that's b, okay? So that's the basic examples for what it is. And the main idea for how you can use the Laplace mechanism is pretty simple, actually. It just says, well, just look at the add noise proportional to the sensitivity, okay? Think about it like this. So if you just run Laplace with lambda magnitude of noise scaling, then you get this much differential privacy. So if you want to achieve epsilon differential privacy, that means that epsilon is equal to L divided by lambda. So that means that lambda has to be L divided by epsilon. Yeah. So the more sensitive the function is, the more noise you add, and the smaller the epsilon is, which means the more privacy you need, also the more noise you add. Okay? And the proof is pretty simple. We just look at the ratio of the two things. Okay? And for one and the other, and there is a minus here, that's why I switched them. And then you just break it up, and just this plus L from the definition of the smoothness. Okay, so we just directly get this. So it's pretty simple. So the question we want to ask now, we will do maybe a short exercise, is what is the effect of applying Laplace mechanism in the local model versus the centralized model? Yeah, it's quite different. Okay. 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 So let's look at this example. Is it visible to everybody, or should I make it bigger?
It's good.
Okay. So okay, let's say we want to calculate the average salary. Okay. 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 We need to have some maximum salary. Okay. If we don't have maximum salary, then we can't use Laplace basically, because we need to have a bound on the sensitivity, and the sensitivity is basically bounded by the amount of salary they can have. Yeah. So if we add one person to the data, then this adds a little bit. Now, how much privacy we want to lose, right? Now, this is the hardest thing we can play with, because we don't really know the meaning of it, right? In the sense of, you can say, okay, they increase the posterior ratio by something, right? But for practical reasons, what does it mean? Do I care if somebody learns my average salary to some accuracy or something like that? Maybe this is more important. Yeah. So we just plug in some number here. No, that's for fun. It could be anything. It could be larger than 1. Yeah, it doesn't have to be smaller than 1. Okay. Now here I don't have a real data, so I'm just plugging in the gamma distribution. If you don't know the gamma distribution, it's basically a distribution from 0 to infinity, and it can have a peak anywhere. Yeah? So it has a shape like this. You can think of it as a warped normal distribution or something. Yeah? It's pretty convenient for anything that has positive values from to infinity, and can have a peak somewhere else than 0. Because something like exponential is always peaked at 0. It's not very useful. Yeah. So for age, maybe, and salary, this is useful, even if it's not a finite bounded distribution. Okay. So now we just generate some data. Okay. Now, we can just calculate the average salary. Just put that in the Python console directly. So we can see it. Okay, so the average salary is 1.9, okay? Now, we remember what we mentioned about sensitivity. So if we have just one mechanism that's local, adds noise to one person's data, then we basically just say, well, just use the formula, add local noise to every person, and noise should be local sensitivity divided by epsilon. That's what we had in the formula. Okay, and we just calculate the average again. Okay, it seems wrong, right? Minus 11. Yeah. So if we look at the individual data, data plus local noise, it's this, right? So people have minus 200 salary and so on. Okay, seems not very nice. Okay, what about centralized? We can do the same thing for centralized. Now we have to add less noise, right? And so 1.3. So it's still not very close, but it's still at least not negative, right? So if we run it again and again, then we see again different values. So let me just try. Oops. So here we got a better value. Yeah, but you can see it's mostly okay for the central mechanism. Yeah. Now, why is that? Right? Well, if you just do a quick calculation, doesn't have to be very precise, you will see that, well, the variance of Laplace is 2 lambda squared, right? Yeah. And lambda has to be sensitivity divided by epsilon, right? So in the first case, we add, well, so the local model, we have to have L divided by epsilon, right? Squared times 2. That's the variance we have for the local model for our average for each one of these, right? But we are averaging all of them, so divide by n. Okay. While for the central model, well, L lambda is L divided by epsilon n. Okay. Wrong here. Yeah, it's fine. So we don't average anything, we just have the average of everybody, and then we add the noise. So our noise variance will just be lambda divided by epsilon n squared times 2. Okay? So it's the same thing, but one is basically O1 over n, and the other is O1 over square n. Yeah. So we need to square the amount of data to have the same error, basically, in the local model as we need for the central model. So this is a problem, but this is unfortunately the only way we can actually do local privacy. You know, we lose something because we don't trust the person that is doing the function. Unfortunately, but if you're thinking about big data problems, it doesn't matter so much anymore. Have 1 million people, then it's probably okay. If you're talking about very small data sets, then it's harder. So basically the lesson of privacy at the high level here is, for the local model, it's harder to be accurate. Yeah, it has stronger guarantees in terms of you don't need to trust everybody. And in other case, if you have a lot of data, then privacy is easier to achieve than if you talk about few people's data. Yeah. So every individual will be hidden more than if they were not. Okay, I guess that's okay for now. And there is one more mechanism to discuss, and then we have open discussion.